Good evening, everyone. Welcome to the second talk of the term at Scientific Society. Today we have the honor of having Professor Peter Atkins with us. I'll give a quick introduction for Professor Atkins and we can get started with the talk. So Peter Atkins is a fellow of Lincoln College in Oxford and emeritus professor of physical chemistry. When first appointed in 1965, his research was in theoretical chemistry and magnetic resonance, but he soon turned to writing and since then had published 70 books. Apart from his well-known physical chemistry textbook, he has written books on science for general public, including Molecules, Galileo's Finger, On Being, and Conjuring the Universe. He retired in 2007, but he continues to write and to lecture worldwide. He's also one of the patrons of our society, and today Professor Atkins will talk about the origins of the laws of nature. So please join me in welcoming Professor Atkins.
Well, thank you very much. I'll begin by saying what I believe to be a law of nature, and then talk about part of the stimulation for this talk, and then maybe after all that I will get to the talk itself. But basically the world is a wonderful but complex place, and what I regard as a law of nature is really the identification of regularities in it. So all the laws of nature are sort of subsumed into quantum theory, into classical theory, and so on, Hooke's law, and so on. It's science's attempt to impose, or at least to recognize, order in the universe. And so there's a really deep question, I think, about where these laws originate. And people have come up with all kinds of ideas. Of course, if you go back to medieval times, by which I mean about 1950 or so on, then people will say, well, it was really imposed on the world as a kind of statement when the universe came into existence, and so that it was an imposition on the structure of the world. But I went to a talk that actually stimulated me to think about the origin of laws of nature. Was given down the road, I won't say exactly where, by a philosopher who is also a theologian, so he's obviously biased in the kinds of attitudes that he takes, unlike we scientists, of course. And he said in the public lecture, that in his view, the simplest possible explanation of the origin of the laws of nature is, for example, that God pushes every electron in the appropriate direction all the time. And he regarded this as the simplest possible explanation of their origin. Now, I think God, if there is one, has got better things to do than to push every electron in the right direction all the time, and every proton and every whatever. And so I tried to think what would my answer be to a philosopher who took this ridiculous view. And I'm spurred by the thought that we scientists are hewers of simplicity out of complexity, that we look at the wonderful world around us and see its complexity, but we accept that it arises from an extraordinary simplicity. And it's the challenge for science, I believe, to unravel the complexity, to find the underlying simplicity. Ravelling it up again so that you can predict the complexity of the world from the simplicity, I think, is a much more difficult problem than unravelling the complexity and going down to the underlying simplicity, because it's all so non-linear and so on. But going down, what I believe a scientist is born to do is to identify the simplicity from which the complexity springs. So I thought to myself, maybe there are three principles that I can use to discover the origin of the laws of nature. I'll use three principles and one hypothesis. And the principles, one is indolence, that nothing happens actively, infinite laziness. The second possibility, if indolence is not adequate for the emergence of the laws of nature, then maybe anarchy is. You allow anything to happen and see whether out of it emerges the laws of nature, a law, any law of nature. And there's always the last resort, of course, of if indolence and anarchy are insufficient, then maybe ignorance will be the origin of a lot of what we know. So I'm going to use these three principles to try to understand the origins of the laws of nature. So I can't think really of anything simpler than indolence, anarchy, and ignorance as my driving power for what I should try to do today. And I need to say a little about the hypothesis I will make, and then sort of justify it, but ask you to at least go along with it, because I think it works. I'm going to talk about the origin of the universe. And that, I mean, if historians among you, if there are any, will see that as a simplified view of what's happened over the giga years. But there is a kind of depiction of the origin and the history, subsequent history of the universe. Now, it's quite possible that we live in some daughter universe of some original universe. And many people, well, I won't say that, but what I want to do is even that we might live there, okay, in that particular universe. But I really want to, but this original universe might actually be where we live as well. I really don't mind. But I want to focus on the origin of that original and perhaps only universe, and say, and to propose the following hypothesis, which might run against intuition, common sense and so on, but basically much of science proceeds by overthrowing common sense. And I want to focus there and to say that really nothing happened. So my hypothesis is that originally there was absolutely nothing, and the universe came into existence, but inherited the properties of absolutely nothing. And by absolutely nothing, I mean nothing at all. So indeed, for quite a lot of this evening, I'm going to tell you about absolutely nothing. and you will go away having learnt a great deal about absolutely nothing, and almost certainly believing in absolutely nothing as well. So what do I mean by absolutely nothing? I don't mean empty space-time. I mean absolute nothing. And the properties of absolutely nothing, I think, is that it's totally uniform. Because I don't think you can have sort of lumps of absolutely nothing which are denser than, other parts of more diffuse absolutely nothing. So I'm presuming that absolutely nothing is totally uniform, which I shall represent like that. I shall also presume that it's totally isotropic. You can go around a point and absolutely nothing changes. Or, as it were, absolutely nothing doesn't change. So you can see where the language sort of gets a bit complicated. And I shall also suppose that it is totally empty. Okay, no space, no time, no nothing, or absolutely nothing. Okay, so that's what I mean, and I think that when the universe came into existence, either this universe, if this is the only universe, or our predecessor universe, the original, the universe, if that came into existence, it came into existence out of absolutely nothing. And I will assert, and this is my hypothesis, which I'm perfectly happy to discuss later, is that when something emerged from absolutely nothing, then that something initially inherited the properties of absolutely nothing. Okay, I'm not denying the Big Bang or anything like that, but I'm saying the incipience of the universe, which was then accompanied by Big Bang, inflation, whatever you want to hypothesize there. There was the incipient universe inherited the properties of absolutely nothing. So my three principles then: indolence, anarchy, and ignorance, and my supposition that the incipient universe inherited the properties of the predecessor, absolutely nothing. So let me talk first of all about the role of indolence, and I'll talk with something which is familiar to everyone, which I think is one of the deepest of all the laws of nature, because so much hangs on it, which of course is the conservation of energy. I mean, causality hangs on the conservation of energy. If you didn't have the conservation of energy, after all, conservation of energy acts like a policeman on events. If you didn't have the conservation of energy, you wouldn't have causality. And if you didn't have causality, you wouldn't have science. And you really wouldn't, there would be nothing to understand. So I think the conservation of energy is one of the great laws of nature, and a pivotal law of nature. And we ought to understand where it comes from. And of course it comes from, the elucidation of where it comes from comes from the mind of Noether, a German mathematician. Mathematicians die either close to zero or to infinity, and she was unfortunately one of the mathematicians who died closer to zero than any higher number, so she died young. Nevertheless, she left behind an extraordinary corpus of mathematics, of which one component I'm going to draw on this evening, which will be known to some of you already, which is known as Noether's theorem. And what Noether established was that wherever you have a conservation law, then there is an associated symmetry. So turning it round to understand where a conservation law comes from, such as the conservation of energy, then you need to identify the symmetry which is allied with it. And the symmetry, Noether's theorem, when it is applied, goes on to show that the conservation of energy is a consequence of the uniformity of time. So if time sort of goes tick, 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 tick uniformly, and I'm speaking, I must, I suppose, insert the following parentheses on a cosmic scale. If time is uniform, then Noether's theorem implies that energy is conserved. If time were not uniform, you know, tick, 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 so on, like it might seem in some lectures, then energy is not conserved, and we would lose causality, basically. So why is time uniform? Well, go back to what I said earlier on. Absolutely nothing is totally uniform. So when time comes into existence at the incipience of the universe, then time inherits that uniformity. So time on a cosmic scale, once the universe has come into existence, is uniform, and therefore energy is conserved. So basically, I'm saying the inheritance of that uniformity results in this wonderful law, the conservation of energy and the consequences of it. There is, of course, the question of where I put the red line. And a part of my argument for nothing happening at the incipience of the universe, I think I prefer incipience to creation, because it really shows that it just casually dropped out of absolutely nothing, but in ways that perhaps we can talk about later on. But where do I put the red line, and so on? From a theological point of view, how much energy did God trust mankind to have? Because once he gave it, you were stuck with it. Let me just say a few words about this. You didn't take this too seriously, but you can see where I'm going. To measure the energy of the universe, then you simply have to weigh a galaxy. That determine its mass. Multiply by c squared, and you get the energy represented by that galaxy. And so you do that for, say, that galaxy. Then you do it for another galaxy and add it to the first sun, and so on. And you can see by the time you've done it for every galaxy in the universe, then you get a really big energy. And philosophers, some, all theologians, would then say, my God, where did it all come from? And why is there just that amount? Well, that's because theologians, and not all philosophers, are circumspect, because there are other contributions to the energy other than the energy represented by the masses of galaxies. After all, when you've got gravitational attraction, you've got attraction of any kind between bodies, then it lowers the energy. So you can see where this argument might go now, that if you take the interaction of that galaxy with that galaxy, then it lowers this energy a bit. You take another galaxy with another galaxy, it goes down further, and so on. And now, if you sort of add in dark matter and dark energy, then I think, and of course this is speculation, I suspect, and I would be surprised if it were not the case, that that total energy of the universe goes down to zero. In other words, where God decided to give us energy, he decided to give us none at all. And in a sense, what happened at the universe, what the incipience of the universe, was not the creation of energy, it was the separation of energy into more interesting opposites, and so on. Okay, so before the incipience of the universe, there was no energy, and after it, now, there is still none. One of the other great laws of classical mechanics, of course, is the conservation of linear momentum. Where does it come from? Noether's theorem tells us where to look. It comes from the uniformity of space. So if space is uniform, then linear momentum is conserved. Why is space uniform on a cosmic scale? Because nothing was completely uniform. The newly formed universe inherited that uniformity, and when space came into existence, it was on a cosmic scale uniform. Hence the conservation of linear momentum, and therefore really the great, together with the conservation of energy, the great tapestry of classical mechanics. Conservation of angular momentum. Remember that I said I regarded absolutely nothing as totally isotropic. Well, if you have spatial isotropy, then by Noether's theorem you have the conservation of angular momentum. So once again, you can see that there is no, to identify that other contribution to classical mechanics, you can appeal to sort of indolence, nothing happening, and inheritance. And once again, how much angular momentum is there in the universe? I think it's zero. I mean, you can make observations on the rotations of galaxies, and they are rotating in all sorts of different directions. But their uniformity is, so the sum of the angular momenta is zero. And so, once again, before the creation, there was zero angular momentum. After the incipience of the university, there is still zero angular momentum. So nothing gets created at the creation. It just gets separated into cancelling opposites. Take charge. This, before the universe came into existence, absolutely nothing had no electric charge. Now we know that there are exactly equal amounts of positive and negative charge, because if that weren't the case, then so strong is the electromagnetic force compared to the gravitational force that the universe would have blasted itself apart before it could really achieve anything interesting. So once again, it's a separation of absolutely nothing into equal and opposite amounts of electric charge. So when the famous early thermodynamicists were studying the conservation of energy, looking at the transformation of work into heat and so on, and establishing the conservation of energy, what they were really doing was not doing experiments like that. They were actually studying the structure of space-time, although, of course, they didn't know it. So let me go away now from indolence and get into the role of anarchy. And the anarchy that I'll talk about, it chooses one very simple law of nature, which is really that light travels in straight lines, more generally, that it travels by the path that is least time. Now, there's a kind of naive puzzle there. There's the source, and there's where we're going to observe it. Suppose instead that light had travelled by this path, and it felt such a fool when it got here, because it wasn't going to be the shortest path of shortest time. It wasn't worth going back to the beginning and starting again. So how did it know initially that this is going to be the path of least time? Well, to answer that sort of question, you need to appeal to the wave nature of light, and to think of a general path, a curved path, as I've got it there. And that path, of course, has nearby neighbours. And notice that the phase at the detector end of the path is quite different. I've represented it by those different coloured columns. And you can see that if we've got another nearby path, then there's going to be all sorts of phases there. So all these phases there is zero amplitude, zero net amplitude at this point if you consider all possible neighbours of any curved path. But of course, if you take a straight line, a straight path, then it has a neighbour, and the phases are very similar. I mean, we're really talking about first-order differences and second-order differences. There are no first-order differences in the phase at this point. And if you add yet another path, nearby path, once again, all the phases are very similar. So in other words, the straight line path does not have neighbours that annihilate it. So, in other words, if you now allow all possible paths, this is anarchy, between source and detector, then every curved path has neighbours that annihilate it. But the straight line path has no neighbours, that does not have neighbours that annihilate it. So in other words, if you allow everything to happen, what you get is basically a law of nature that, crudely speaking, light travels in straight lines, and more generally, that Fermat's principle of least time. And of course, so you get effectively geometrical optics out of anarchy. Geometrical optics is a manifestation of electromagnetic anarchy. And you can see the same thing for particles as well, because after all, before 1927, when people were struggling with the concept of electrons, for example, or as particles, and the transition came when they were realised that after 1927 they do have wave character, and we're in the domain of quantum mechanics. Incidentally, I think what I'm actually plotting here is a particle with linear momentum to the right. People normally draw them as up and down waves like that, but all real waves are stationary, whereas complex waves have directionality. So you should really plot the real part of the wave function against the imaginary part of the wave function, and that gives you this helix, and the screw sense gives you the sense of travel. Take the complex conjugate and it goes the other way. So once again, we've got waves representing particles, and just to remind you, if you're not quantum mechanics, that the greater the amplitude of the wave, the greater the amplitude of this helix, then the greater the probability density of finding the particle in a particular region. So as the amplitude goes down, the probability density goes down, and if you've got no wave, then you've got no probability density, no probability of finding the particle in a particular region. And so you can see how the principle of least time carries over into particle mechanics once you realise that particles actually have wave character. Any straight line path of a particle any curved path of a particle has neighbours. It's got, you're English, you've got Scotland and France, so they're annihilators. But if you take a straight line, then all your neighbours actually are sort of conciliant and don't annihilate you. So in a sense, and this of course was an approach to quantum mechanics developed by Feynman, in instead of talking about the phase, you talk about the action associated with a path, then the whole of quantum mechanics is another manifestation of anarchy. You allow particles to go everywhere without constraint, and the paths that survive to be recognized in this world and therefore incorporated into laws are the ones that survive that sort of thing. So there we are, once again, anarchy and law. So really this is a summary of that kind of corpus of ideas, which I won't go into in detail, just more or less summarizing what I've been saying. What about the laws of electromagnetism? I need to share with you my shallow understanding of gauge theories. Gauge theories, a gauge is simply a ruler. So basically, a gauge theory does that to a wave. I mean, smart names. I mean, theoretical physicists are really smart at PR by choosing names which sound awe-inspiring. But when you take off the covering, you find that they're just talking about rulers and things in a very clever way. There we are. So there's a gauge. And I can move that blue helix to the right. That is, I really just changing the gauge. But notice that nothing happens to the amplitude. So that follows that nothing happens to the physics either. The probability of finding the particle, which described by the blue wave in a particular region, is exactly the same as finding it in the if it was described by the yellowish wave. In other words, the physics is gauge invariant, independent of how you measure it with a ruler, if you like. So I'm talking about gauge invariance as another symmetry of nature. And you can see that by global gauge invariance, I mean I take that wave and I shift it from blue to yellow uniformly throughout space. And you can see that the effectively now what is flowing into this side of a region is matched by what is flowing outside that region. And so there is a conservation of electric charge, with the electron carrying its electron charge. So global gauge invariance is really the origin of the conservation of electric charge. And so going back to the remark I made earlier on, it's absolutely nothing had no electric charge. It's separated when the universe came into existence into red and green, opposite electric charges. And we know that the total electric charge of the universe is still zero, and that electric charge is conserved. So really, we'd simply look for the gauge invariance as another symmetry that we need to think about. But this wave function, of course, satisfies the Schrödinger equation, and this displays the equation in enough detail for what I'm doing this evening. But suppose we take that wave and we change it in the way that I've described already, then it remains true that that satisfies the Schrödinger equation. But suppose I do something different. Suppose I move the phases by different amounts in different locations. And as you see, I've sort of scrunched up the spring here, stretched it out in other places. Still, the amplitude remains the same, so the physics remains the same. The probability of finding the electron, as described by that wave, remains the same when it's either described by the blue or the yellow waves. But that scrunched up wave no longer satisfies the Schrödinger equation. In order to find an equation that it does satisfy, you have to add a bit to the original Schrödinger equation, and the bit that you have to add is effectively equivalent to the Maxwell equations. So local gauge invariance therefore implies the laws of electromagnetism. So once again, you can see how the inheritance of uniformity in some rather more abstract sense now is leading to the laws of electromagnetism as established, for example, by Michael Faraday, and which sort of drives the modern world. I'll move on from anarchy to the last resort of every scholar, namely ignorance. And how does ignorance this time come into play? Well, it comes into play in all sorts of different ways. I'll spend only a tiny amount of time on this bit. If you've got a potential energy with position, then it varies in general like that. And the first derivative, of course, is the absolute value is 0. There is no first derivative, but there is a second derivative. So any general curve has a parabolic minimum or maximum, unless it's constrained in a special way in some kind. And of course, once you've got a parabolic potential energy, then you have, by implication, Hooke's law and the behavior of oscillating bodies and so on. So Hooke's law is an extraordinarily deep law, but it really stems from ignorance about the potential that a particle is experiencing. The gas laws, I won't go into them, they're too boring, but they're once again, it shows the constructive power of ignorance, that by not knowing what the particles are doing in this container, you obtain the laws of Boyle and Charles and so on. Once again, ignorance is a constructive factor for leading to laws. And of course, the greatest representation of ignorance is the Boltzmann distribution. Because to understand the Boltzmann distribution, think of the array of available. And I like to think of Boltzmann lying on his study floor, all his books around him, and his bookshelves on one wall, nonchalantly tossing the books at his bookshelves, hoping that they'll line up on the shelves. And it's extremely unlikely, it would be to his surprise, that he got that. That's an outcome of very low probability, of course. Do it again, and you might get something like that. Much higher probability to get a distribution that is like that. But if he was doing it trillions of times, then, of course, what he would get, the most probable outcome, would be that distribution, which we all know as the Boltzmann distribution. And the Boltzmann distribution arises purely from ignorance. None of those shelves, none of those energy levels has anything that is attracting the balls and so on. Boltzmann, is tossing them up. Of course, it's ignorance in alliance with the conservation of energy, but we know where the conservation of energy comes from. It's back in the days of indolence. And of course, what the Boltzmann distribution does is to provide us with an understanding of almost everything. And I think if I were to choose an intellectual companion on a desert island, this is an intellectual desert island, then I would choose someone like Boltzmann, because he, through the Boltzmann distribution, arising from ignorance, you can understand really just about everything to do with chemistry. That high temperatures, the red curve, high energy levels have got substantial populations, so reactions occur. Low temperatures, when all the populations are in the lowest energy levels, you have stability because the molecules don't have enough energy to do anything but to simply be. Now, I wouldn't want to be on a real desert island with a real Boltzmann, since he was a depressive. That might be like being on a liner anchored off Japan at the moment, wouldn't it? Be confined to your inner cabin for 14 days. But he did kill himself in the end because people didn't understand what he was trying to say. Anyway, so there's ignorance comes into the Boltzmann distribution, and the Boltzmann distribution underlies so much of what we do in not just chemistry, of course, but physics and biology. They're all the same, really, of course. But let me just say a few words about why anything happens at all, because we know that all sorts of nasty things happen out in the world. And, of course, I'm now talking about the origin of the second law of thermodynamics. Effectively, we dealt with the first law, with the conservation of energy, although, of course, the second law is got knobs on. Oh, I ought to say, by the way, that the Boltzmann distribution and its origin in ignorance introduces you the concept of temperature, because this temperature is that parameter that occurs in the exponential curves that I was drawing. So out of ignorance also comes the understanding of that elusive concept of temperature. But okay, the essence of the second law. Effectively, the second law says that this doesn't happen. Mm-hmm. What the second law says is that things get worse. I mean, that happens. And I think it's, although there are questions of time reversibility in the laws of nature that you might want to probe later on, the fact that summarizes the driving power of the universe when things simply get worse. They don't get better unless you really do work on them. So things get worse, but the point of the second law is that there might be a mechanism that links into that getting worse and drives another process, a process of getting better. So all the second law says is that if overall things get worse, there might be local abatements of chaos and structures can emerge. So this might be the hydrocarbon fuel of an internal combustion engine. These might be the carbon dioxide and water molecules, and which are dispersed, which disperse. And this also represents the energy released in the combustion that also disperses into the environment. This might be the real engine, and this might be a pile of bricks or stones, and from it you build a cathedral. So you can see that although the world is getting worse locally, there can be local abatements of chaos. That, let me go back a stage. Don't go back, never mind. This might be breakfast. This might be digestion. This might be the metabolic processes in your body. This might be amino acids, which are built into this highly structured molecular cathedral. This enzyme, this protein, whatever. So you can see that as you eat, so you grow. And so the second law enables you to pursue the connection between the great disperser in the sky, the fusion processes going on here, and the energy dispersing through the solar system, being captured on Earth by driving photosynthesis and forcing, if you like, that local abatement of chaos that we call the biosphere. And then the biosphere, or bits of the biosphere, being breakfast, leading to the formation of not only proteins, but the proteins that congregate into organs that enable you to think about the nature of reality. I've got a few minutes left. I didn't mention tradition in my original opening remarks, but you might want to think about something closely related to the laws of nature, which is the values of the fundamental constants. Where do they come from? So what is the origin of the values of the fundamental constants? Is it possible to simplify our understanding, not necessarily to identify their actual values, but to simplify our understanding of their origin? Well, I think there are two classes of fundamental constant. There are the structural constants, which are things like the speed of light, and Planck's constant, and Boltzmann's constant, things like that. And there are the, which gives really the constants that are core to relativity, to quantum theory, and to thermodynamics, the three great streams of understanding of the world. And then there are the coupling constants, the fundamental charge E, the gravitational constant, strong, weak constants, and so on, which give rise to the coherence, if you like, of the universe. I have no idea about the origin of the values of the coupling constants, and it is quite possibly, and almost certainly, let me say, the case that they are changing with time. So they're more elusive as you know, as the universe cools. These the coupling constants, fine structure constant, and so on, might well be changing. But I think the structural constants you can identify where they come from, and I think you can give them all their actual numerical values. Because mankind, humankind, womankind, whatever, has been led astray by a variety of things. I'm sorry, let me. So I'm not going to talk about the coupling constants. You can see where I'm coming from. I'm going back to this picture of the mechanical equivalent of heat, of work, of heat that so exercised the early thermodynamicists. They established that work was proportional to heat, putting it crudely, and they identified this value of the mechanical equivalent of heat as that value. Why did it have that value? Why is that got such a funny value? They were so stupid. And they were stupid as mankind was stupid, in a much more general sense, as I will show, by measuring work in one unit and calories in another. They're both manifestations of energy, so why not use the same units? And of course, as soon as you do that, then the K becomes 1. So the mechanical equivalent of heat, when you measure both transactions of energy as heat or as work in joules, it's 1. So all the work that they did in this careful determination of 4.18 and so on, completely useless, completely a waste of time, because K is obviously equal to 1. It's just that choice of units that might have been convenient to talk about heat and work in different units, but led to this misunderstanding that here was a fundamental constant that needed to be explained. What about the speed of light? That value. Why does it have that value? Well, a meter is defined as that fraction of a second of light travel time. So I'm about 6 nanoseconds tall. Why not measure distances in seconds? Okay. And if you measure distances in seconds, you get some awkward numbers maybe, but 6 nanoseconds is not much different from 5 for 8 or something. I mean, it's all sort of understandable. The speed of light, with the definition of a meter, these days a meter is defined in terms of seconds of light travel time. There is the calculation you have to do, and you see it comes to 1. So the speed of light is actually 1 if you're sensible and measure space and spatial distances and temporal interludes in the same units. Just like mechanical equivalent of heat, it vanishes. You don't need it anymore. So, and why? Well, some people said it was because there was a kind of viscous drag, but we know that's how I'll skip that. And of course, why 1? And that 1 is related to the way that to different observers travelling at different velocities, space and time become interchanged, and you really can't go beyond 1 when time has completely been rotated into space. Planck's constant. Why has it got that value? Well, because we happen to measure energy in one unit and frequency in another unit. Why not measure them all in the same unit? And if you do that, express energy as a frequency, then H obviously becomes 1. Nothing to explain. Boltzmann's constant. There it's conventional value, but notice that we've got joules and kelvins. Suppose we can express temperature, not in kelvins, but in joules, or inverse joules, or whatever. Then if you do that, and you follow the arithmetic through, you express the temperature as an energy, and therefore as a frequency, as we did in the Planck's constant bit. And so Boltzmann's constant becomes 1. You don't have to explain these funny numbers. You just have to choose coherent units, the same units for everything. And I think using seconds and the inverse seconds for frequencies and so on, really does away with all these funny numbers and leaves you with nothing to explain. And I think science is all about finding ways of using nothing to explain something, or indeed finding that something leaves nothing to explain. So, thank you very much.
Thank you, Professor Atkins, for such an intriguing talk, and I'm sure we all learned a lot about absolutely nothing and fundamental laws of nature. So we have a few minutes for questions, and there's a microphone at the back, so we can pass it around, or you can be loud enough. So are there any questions?
I thought that was a very, very interesting talk, actually. I hadn't really thought about it in that way before. In fact, as I was going through, I was trying to think of anything that you couldn't kind of relate to your kind of principles. I suppose one thing, and you mentioned the coupling constants as being one kind of thing that's tricky to explain, but maybe something else, which I'm trying to think it may be related to the coupling constants, is what about if you kind of talk about the number of, say, particles we see in the standard model and stuff? It seems to be some of this random number.
Yeah.
I don't think, is there a way to kind of relate that to some kind of the symmetry of nothing?
Well, almost certainly, I would have thought. But and it's obviously, I think it's probably related to the values of the coupling constants as well. But I have no views on how many there are and what they are and so on. But it would be interesting to look into gauge theories to find what emerges. Yeah.
How would matter revert to nothingness? Is it with antimatter?
Well, matter is the same as energy. I mean, it's just a localized form of energy, basically. So E equals mc squared. I mean, if C is equal to 1, then E equals m. And so, effectively, you should think of matter, mass, as really as a measure of energy. Yes?
I'm not going to get into any philosophy right now, but I was thinking about quantum mechanics. That also seems to be explainable by your anarchy method.
Yes, well,
it's basically the same thing.
Yes, effectively. I mean, that's it's Feynman's path integral method that I was alluding to, where instead of the phase length, you talk in terms of the action, and the equations are all very similar.
It's interesting to note the question of if there is even any choice. So for most physical theories, you can kind of imagine changing the equations a little bit, and then typically you find that you break some symmetry and that's bad. General relativity is fairly floppy. You can do a lot of stuff. Quantum mechanics seems to be unusually rigid.
Yes.
It's kind of almost peculiar how few choices there are about it.
Yes, and extraordinarily precise in its predictions. And so it is a rigid theory, and maybe it is general relativity that will have to bend before, in order to marry the quantum theory. Yeah.
It's easier to bend general relativity.
Yes, just so. Yeah.
How would we explain time from nothing?
Well, yes, I think I can. In the following sense, this will take me into a domain I don't want to go into in this talk, which is how nothing can turn itself into something. And I think effectively you can understand why time is one-dimensional, for which there is ample evidence, okay, not two-dimensional and so on, because you can't turn round in one dimension, but you can turn round in two dimensions. And it's the direction of time that distinguishes a particle from its antiparticle, if you like. So the universe acquires stability only if time is one-dimensional, would be my view. But I would need to elaborate that to make it more plausible. But you can see where the argument might come from. So that time is something that distinguishes, in a rather philosophical way, being from non-being. And because you can't turn around once you've got it started in one particular direction, being and non-being can't coalesce back into nothing. So you can begin to see perhaps a germ of an idea there.
Time for one last question. Yes.
In your book, Creation Revisited, You mentioned you had a section that talked about building things from empty sets, and sort of that being a possible model for the incipience of the universe. Is that still a part of your sort of canon of ideas?
Yes, I think so. That thought is stimulated by the recognition that mathematics is such an extraordinarily useful way of describing the universe and everything that goes on in it. So is there more to mathematics than just usefulness? You know, is the world deep down mathematics somehow rendered tangible? And so you look for how mathematics emerges and use the empty set and the sets that contain the empty sets to generate the integers. And once you've got the integers and you do nasty things to them, you've got mathematics. It might be garbage, but it could be that there's a deep connection there.
Okay, let's thank Professor Atkins one last time for answering all the questions.